So if we had 3x plus 1 equals -7, here's the variable that we want to get by itself. It is currently part of this 3x, which means in order to get to the x, we got to get to the 3x first. How do we get the 3x by itself? We got to get rid of the plus 1. So what's happening to the 3x? 1 is being added. We're going to do the opposite. 1 should be subtracted. Cancels on the left, just leaves us with the 3x. On the right, -7 minus 1 is -8. Then, what is happening to the variable? Times 3. How do we get rid of times 3? Divide by 3 on both sides. If it doesn't divide evenly, we leave it as a fraction. So the 3's cancel on the left, and we're just left with x. On the right, -8/3. So -8/3. Let's do another one like this. (3x plus 1 equals -7). We're going to go ahead and subtract 1 from both sides. Oh, sorry, that's the one we just did. Sorry. Thought that looked familiar. I meant to say 5x minus 19 equals -23. So we want to get to the x. The x is trapped currently with the 5x. So how do we get that by itself? We got to get rid of minus 19. If subtracting 19 is happening, we do the opposite, add 19. And we do that to both sides. That cancels on the left, leaving us with just the 5x. On the right, -23 plus 19 that's adding two numbers with different signs. So I'm going to do 23 minus 19. That gives me 4. Since the larger number was 23, it came from a negative. That means my answer's going to be negative, -4. Now we want to get the x by itself. We need to undo multiplying by 5. So we divide by 5 on both sides. So our answer is x equals -4/5. We can make it even more complicated. And let's take a look at negative 3 times, in parentheses, w minus 4 plus 5 equals 10 minus, in parentheses, w plus 1. So our old friend, the distributive property, is coming around again. Remember, with algebraic expressions, the rule was clear parentheses by using the distributive property. We're going to do the same here. So that negative 3 is going to go through. 2 terms on the inside, so it's going to go through twice. And over here, this minus, the negative, is going to go ahead and get distributed through. Remember, distributing the negative is like taking the opposite of the term, or you can consider it multiplying by negative 1, because that's really what's going on there. A negative 1 is getting multiplied by each, but multiplying by negative 1 is just taking the opposite. Remember, pay attention to your signs. Negative 3 times w would be negative 3w. Negative 3 times, the sign goes with it, negative 4. Negative times negative is positive 12. We don't do negative 3 times 5. That 5 is not in the parentheses. It's not involved with the distribution at all. It just carries down. Over on this side, the 10, not involved with the distribution. It's a separate term. It just carries down. Now distribute the minus sign. The opposite of w. The opposite of positive 1. So negative 1. Negative w. The opposite of w. Negative times positive is negative. So it just changes the sign on everything in there. Now we combine like terms. Remember, when we were dealing with the algebraic expressions, first clear the parentheses with distribution, then combine like terms. When we're solving equations, that is an expression equals an expression. And we're going to simplify both of them as much as possible before we start adding things to both sides. So just because you see an equal doesn't mean you're immediately going, oh, I see plus 5, so I'm going to minus 5. You don't want to worry about any of that until both sides are as simplified as they can get. So on the left, there's no more w's. That minus 3w is just going to hang out by itself. But we have positive 12 plus 5. That is positive 17. So plus 17. Remember, our positives and our negatives make up our pluses and our minuses. Over here, we got a positive 10 minus 1. This minus has nothing to do with it. That minus goes with the w. These are not w terms, so that might as well not be there. 10 minus 1 is 9, positive 9. And then that minus w carries down. Okay, we cannot simplify the left anymore, and we cannot simplify the right anymore. At this point, our next step is to get all of the variable terms on one side and anything without a variable on the other. But we can't just pick them up and move them. We have to use our opposites. So I like having w's on the left and the non-w's on the right, which means I need to get rid of the w on this side. How do I get rid of subtracting w? I'm going to add w, but whatever I do to one side, I have to do to the other. That's just going to cancel over here on the right and leave me with just a 9. Over here, -3 plus 1 would give me -2 W's. -3W plus 1W. -3 plus 1 is -2. So -2W plus 17. So see how this works? Now there's only W's on the left. I'm going to get rid of this plus 17. Because to get that W by itself, I got to free it from the -2W. So I got to get the -2W by itself. Get rid of plus 17 with minus 17. Just cancels on the left, leaving me with the -2W. And on the right, 9 minus 17, that's going to be -12. No, that's not right. -8. So now all I have to do, I'm just going to bring this over here. -2W equals -8. To get the W by itself, I'm getting rid of multiplying by -2. That's dividing by -2. Cancels, leaves me with W on the left. Negative divided by negative is positive. 8 divided by 2 is 4. So W equals 4. And remember, you can check your answers. So if you have W equals 4, you can plug in 4 for W everywhere and just check. 4 minus 4 is 0. 4 plus 1 is 5. -3 times 0 is 0. Plus 5 equals 5. It does check. So W equals 4 was the answer. If we ever solve an equation and we get something equal to itself, the same on both sides, not checking it, not getting our answer and then plugging it back in to see if we're right, but in the process of getting our answer, if the variable disappears and we just have a true statement, 3 equals 3, we have an identity. An example of such things now, there's no way to know when you start that you're going to get an identity. You just have to be able to recognize it when it happens. Okay, let's solve this for C. Well, first we'd clear parentheses and combine like terms. So distribute. 5 times 3 is 15. 5 times C plus 2. Combine like terms here. 2C plus 3C is 5C plus 17. Still got one more thing we can combine here. 15 plus 2, so 17 plus 5C equals 5c plus 17. And maybe right here you notice this is the same. But our next step in solving, clear parentheses, combine like terms. Once you can't combine like terms anymore, to get all the variables on one side. So I'm going to go ahead and subtract my 5c from here, from both sides to keep it balanced. But look, all the c's go away. And it says 17 equals 17. This does not mean that the answer is c equals 17. This does not mean that. There is no more c. The c's are gone. 5 minus 5 is 0. 5c minus 5c is 0c, 0. But we're left with 17 equals 17, which is an identity. When this happens, the answer is all real numbers. Or you can just have the set big R, all real numbers. That means that you can plug anything in for C and it will always be true. That doesn't mean that if you have the wrong answer, since you can plug it in and check and it works out and it's right, that doesn't mean you're right. If I put 17 in, it would work. But if I put 2 in, it would work. If I put -8 in, that would work. All real numbers would work, so all real numbers is the answer. And we know that because we get the same thing. The opposite of an identity is a contradiction. So up until now, we've had conditional equations. That means we got one answer. It's only true if this answer, or maybe there's one that has a couple answers. We don't do any of those in this class. But there's a small finite number of answers to the equation, and those have to be what the variables are, or it's not true. Now we have identities. Those are ones when we get a true statement at the end with just numbers, and they are always true. So all real numbers. The opposite of an identity is a contradiction. In other words, you'll get something that is never true. For example, two times -5x minus 1 equals 2x minus 12x plus 6. If we solve here, distribute to get rid of the parentheses. 2 times -5x is -10x. 2 times -1 is -2. Equals, combine like terms. 2x minus 12x is -10x plus 6. I'm going to go ahead and add 10x to both sides to move my x's from the right to the left. Gets rid of them on the right, leaving me with just a +6. But it also gets rid of them on the left. All variables are gone. And I get -2 equals 6. This is not true. This is a contradiction. This means no matter what you plug in, you're never going to get a true statement because -2 does not equal 6. And the answer is the empty set, or no solution. Okay, that's it for this session. I will see you next time. Let's just introduce inequality symbols, introduce inequalities overall. So any two numbers can be written on a number line. And if we wanted to compare the two numbers, three would come before 10, three would be to the left of 10 physically. That's going to be our definition of less than. If we say 3 is less than 10, we mean 3 is to the left of 10 on a number line. If I change that to -3 and put a 0 in between to represent -3 and +10 on the number line, since -3 comes before 10, since -3 is to the left of 10, we can say -3 is less than 10. All negative numbers would be less than all positive numbers. So any negative would be less than any positive because all negatives are located to the left of all positives. If we were just dealing with the negative numbers, though, what's something that comes in between here? Well, 0, -1, and -2 come in between. One might be less than 3 because 1 is to the left of 3, but -3 is less than -1 because -3 is to the left of -1. So in general, if we have A is less than B, some other interpretations might be B exceeds A. If 3 is less than 5, for example, 5 exceeds 3. If A is less than B, that also means B is greater than A. The flip of the less than symbol is the greater than symbol. And if something is less than something else and we switch it, we have a greater than correlation. B is greater than A. If 3 is less than 5, we switch the whole thing. 5 is greater than 3. Notice Pac-Man will always eat the larger number. So the big end of the sign always faces the big number. The point, the small end of the sign always faces the small number. That's why when we flip the whole thing, we still have the same result, but instead of less than, we can say greater than. Here, if we actually look at A is greater than B, that again would give us B is less than A, or we can say A exceeds B. Exceeding meaning being greater than, using the word to define here, but to exceed something means to be greater than it. Now, these aren't the only inequality symbols, less than and greater than. If we put a line underneath, we add on we add on or equal to. So when would we use this? Well, 5 is less than 5 would not be true. However, 5 equals 5, that is true. So to make this a true statement, instead of using less than, we would use less than or equal to, because that's true if it is less than, if it is less to the left of on the number line, or it would be true if it's the same value. So the line underneath changes it from just less than or greater than into less than or equal to or greater than or equal to. If we have A is less than or equal to B, it also means A is at most B, or A is no more than B. So if we're doing word problems and we see is at most or is no more than, these mean less than or equal to, sorry. Less than or equal to. So if we look at a couple things that are true for less than or equal to, 3 is less than or equal to 5. 3 is less than or equal to 3. And 5 is less than or equal to 5. These would be 3 true statements. 5 equals 5, so that's true. 3 is less than 5, so that's true. 3 equals 3, so that's true. So using these values, let's look at these English ones. A is at most B. So that would mean the first thing is at most the second thing. Is 5 at most 5? Yes. It's at most 5 because it's not higher than 5. Is 3 at most 5? Yeah. It's at most 5 because it's not higher than 5. See, I'm using the other one as sort of an explanation, because in English, when you use these words, when you think about what they mean the same thing. Is 3 at most 3? Yes, because it's not any more than 3. So if you see at most or no more than, and you're translating, that's going to be less than or equal to. If we flip that sign, A is greater than or equal to B. A is no less than B. A is at least B. These are translations that mean greater than or equal to. If you see these in a word problem, you would use greater than or equal to. So what kind of word problems? You need to build a fence that will encompass an area that is at least 300 square yards. At least 300 square yards would translate to greater than or equal to 300. Anything that's greater than or equal to 300 would be at least 300. Is 100 at least 300? If I tell you to go to the store and bring me at least 300 and you bring me 100, I'm going to be mad. Why? Well, because 100 is not at least 300 and 100 is not greater than or equal to 300. Now, if I said, bring me no more than 300 and you brought me 100, that'd be fine. Why? Because no more than, that was less than or equal to. And 100 is less than or equal to. It is no more than 300. So translating phrases into inequalities, you have to understand the English words. So a tropical storm is updated to hurricane status if the sustained wind speed W is at least 74 miles per hour. So a tropical storm gets upgraded if W is at least 74 miles per hour. What would the inequality be? Well, you don't have to remember specifically from what I just showed you. You don't have to memorize that. The reason I said just talk it through in English, well, if I said, and even though we're talking about winds and hurricanes, I'm going to keep sending you to the store. If I said, go to the store and bring me at least 74, could you bring me 74? Yep, because that's at least 74. So that brings in our or equal to. If you bring me 73, would 73 be at least 74? No. If you brought me 73 and I asked for at least 74, that would make me mad. If I asked for at least 74 and you brought me 75, that'd be cool. That'd be fine. If you bring me 75, that means you brought me at least 74. These are numbers greater than 74. No, sorry. These are numbers greater than 74. We put the greater than sign in. You know how I knew I was wrong right away? If I put this, as I was saying, numbers greater than 74, well, Pac-Man, if there were numbers greater than 74, why is he eating 74? If it's facing this way, 74 is the big number. So since the numbers would have to be 74 or more, greater than 74, we put our greater than sign in. And we have or equal to because 74 itself is at least 74. Okay. Hurricanes are categorized according to intensity. On a scale of 1 to 5, a category 5 hurricane has the most destructive winds. You thought you were just getting a math lesson today, but here we are talking about hurricanes. A category 5 hurricane has sustained winds W exceeding 155 miles per hour. So we know we're going to have W on one side. We know we're going to have 155 on the other. Our question is, what sign are we going to put in? Well, wind speeds that exceed 155, 156, 157, 158, you can agree these all exceed 155. These are numbers greater than. Pac-Man would be eating the greater numbers. The open end of the inequality sign faces the larger numbers. So the question is, do we put the or equal to or not? Well, if you have a wind speed of 155, by the English language, that does not exceed 155. Exceed 155 means more than. It doesn't imply that a speed of itself would exceed it. So this is just good old-fashioned greater than, not greater than or equal to. A category 4 has winds of at least 131 miles per hour, but no more than 155 miles per hour. So here our speeds are between 131 and 155 because it's at least 131 means 131 is the minimum I would accept. If I sent you to the store, there you go to the store again. If I sent you to the store and I asked for at least 131, the smallest you can bring me is 131. Now, normally we might write it like this. If the smallest is 131, that means things greater than or equal to 131. But I'm going to write it as a less than or equal, and it's because the other side says that it also has to be no more than 155. Things greater than 155 would not be okay because I'm asking for no more than 155. So 156 would get you yelled at. I'd throw papers. 155 would be okay. That would be the highest we could go. And anything smaller than. Since it would have to be both greater than 131 and less than 155, we can write it in between. In this case, it's between and including the values, because 131 itself is at least 131. It's also no more than 155. 155 itself is no more than 155. It's also at least 131. Anything higher would not count. Anything lower would not count. And we'll talk more about these compound inequalities in a little bit. Let's do a little more with talking about whether numbers are greater than, less than, greater than or equal to, less than or equal to. In these examples, we're specifically just going to look for less than or greater than. We won't need the or equal to's to be involved here. And this first one's going to be pretty straightforward, -2 and -5. So let's find them on the number line. If we had a number line, there's 0, -1, there's -2, and -5 would be somewhere over here. Remember, being to the left means being less than. And here we have them on the other side, so we're going to keep the big end with -2. Think about Pac-Man. He always eats the bigger number. So he's always going to be facing -2. See, I can keep math fun. Pac-Man, that's video games. Now I'm just making math video games. Hope you bought that. Okay, so we're going to put in greater than. Like I said, this is straightforward because we can just pull it straight from a number line. But in our next one, let's take a look at two fractions. 4/7 and 3/5. And we want to know whether we can put in less than or greater than. Well, we can't just go, oh, the big numbers are over here. 4 is bigger than 3 and 7 is bigger than 5. That means that this is greater than. It might not be. In order to be able to compare two fractions, we need them to have their common denominator. So for 7 and 5, we would be looking for the first number in common to both. So 5, 10, 15, 20, 25. I'm wondering if maybe there was one before 35, but there is not. 7, 14, 21, 28, 35. So 35 is the common denominator. How do we get there? 7 times 5 gives us 35. So we do 4 times 5. 4 times 5 is 20. Here, 5 times 7 is 35. So we do 3 times 7. And look at that, that's 21. 20 is less than 21. We can compare them because the bottom is the same, and we can only compare when the bottom is the same. The top being the same doesn't tell us anything. It has to be the bottom, because now we're comparing 35ths. 20 of them is less than 21 of them. And since that's what we can put here, that's what we would put here, because these are exactly the same. Same problem. Make sure that's at a point. 4/7 is less than 3/5. Let's do another one of these. Let's do 1/4 and 2/9. My counting by fours: 4, 8, 12, 16, 20, 24, 28. Oh, not 28. Oh yeah, I'm doing 4. 28, 32, 36. There we go. I was expecting to get to my number already. And if I count by nines, 9, 18, 36. I skipped one. 27, 36. First number in common to both, 36. Okay. So let's rewrite them as their fraction over 36. 4 times 9 is 36. So we do 1 times 9 is 9. 9 times 4 is 36. So we do 2 times 4. And we get 8. So greater than. 9 is greater than 8. Since these are the same as these, that means 1/4 is greater than 2/9. Still just comparing with less than or greater than. Let's take a look at 2 and -12. Any positive number is greater than any negative number. Okay, that one was nice and quick. How about that? One of them is a terminating decimal and one is a repeating decimal. This one is negative 1.3 and this one is negative 1.33333333. To help us imagine that, I'm going to skip the imagining. I'm going to write out another 3 there. And the reason I'm going to do that is because over here, the digit that comes after 3 is not 3. It would actually be 0. It'd be as many zeros as we want. To compare decimals, we go digit by digit. The negative ones are the same decimal point. The 3s are the same. The first one that's different is this 0 and that 3. And since 0 is less than 3, less than is what goes in there. I'm sorry. That was wrong. And again, this is why it's important when we're working with negative numbers that we remember we're working with negative numbers. Things don't just magically work the same on both sides of 0. So I went through to compare these and I said, the negative 1 is the same on both. And I kept going. But what that does is it overlooks that on the other side of 0, things work the opposite of the way that they should. So since we're on the negative side, it is true that 0 is less than 3. But on the negative side, we flip that around. And this would be a greater than sign. Would be a greater than sign. If we actually think of where we are on the number line. So 1.33 would be a little bit to this side. 1.3, and then after that somewhere 1.33. But the numbers would be flipped, 1.3 and 1.33. It would now be on that side. So the 1.33 gets the little point. The 1.33, when we're on the negative side, gets the little point. So it hit me that I was wrong because I was thinking about what would happen with our next example. And then I realized, wait a minute, why am I treating this as if it's new? All I'm doing is flipping what side the extended one's on. So our next one, we're going to compare negative 7.2 repeating, which is negative 7.22 and so on. And here, this is negative 7.20. So same sort of thing. The 7s are the same. The 2s are the same. This is the first place we're different. Normally, 2 would be greater than 0, but we're on the negative side, which means the negative 2 is actually going to be less than the 0. And that means we have less than here. So before I was writing this one out, I thought that through and I went, wait a minute, well then how is this less than and the other one's less than as well? And that's when I'm like, well, that means the other one must not have been less than. And sure enough, I was wrong. The last one should have been greater than. Now I want to talk about something called interval notation. I'm sure that in your entire math career, this is not the first time you've seen points on a number line. And maybe you've seen before now that there can be a difference between a filled in point and an open, an unfilled point. If I shade everything to the right, and notice when I'm shading, when I get to the end, I fill in the arrow tip as well to indicate that the shading would continue forever in that direction. The shading is X. The shading is your variable, okay? So if we're looking for X here, X is everything to the right of 5. It's everything greater than 5. X is greater than 5. And when we have the point filled in like this, that actually means greater than or equal to. The one that's not filled in, that's just normal greater than. It means that 5 would not be a solution. The fact that 5 is an open circle is showing us specifically 5 is not shaded. If 5 was shaded, if we could be equal to 5, then the 5 would be filled in. We could be equal to 5. So here, X is everything greater than 5, but not equal to. The shading is X. X is greater than, but not equal to 5. So maybe you've seen filled in an open circle before, but what I'm here today to tell you is that filled in circle can also be represented with a square bracket facing the direction of the shading, so that this would be a left, an opening bracket, and then this is the inside stuff. And the open point, that one can be written as a parenthesis, again, facing the direction of the shading. The shading would be inside this open parenthesis. That's the starting point. So let's think about This square bracket, this parenthesis, and square bracket will go the other direction. So this, the shading is everything less than -2. X is less than -2. It's not equal to because it's a parenthesis and not a square bracket. Here, the shading is everything less than 5. The shading is X. X is everything less than, 3, not 5. The shading is everything less than 3. X is everything less than 3. X is less than 3, but it's also possibly equal to 3 because this is a square bracket. Square brackets are the or equal to. So why am I making a big deal of showing parenthesis and square bracket when we already have a perfectly good open and closed circle system? Well, it has to do with this thing I said I'd show you, this interval notation. Let's say we had 2 is less than X is less than or equal to 7. On a number line, if we just used our open circles and closed circles, we would have an open circle at 2. We would have a filled in closed circle at 7, and X, the shading, would be everything in between, but not equal to the 2. Yes, possibly equal to the 7. If we did it with our new symbols, 2 and 7, a parenthesis and a square bracket. I'm going to copy this down here. A parenthesis and a square bracket at 2 and 7. Filling in everything here. This shows us directly that we have an answer, the interval from 2 to 7 with a parenthesis on the left and a square bracket on the right. This is the answer in interval notation. And this is standard or inequality notation. We can put inequality notation into set builder notation. What is set builder notation? Well, this uses the braces inside braces the set of all X such that vertical bar X is between 2 and 7. So the inequality isn't a set itself. The inequality can be used in a set, in set builder notation. Interval notation, that is a set. I underlined that twice and the emphasis got lost. There we go. That is a set. So this is why we use interval notation a lot in math. It is a shortcut way of delivering this same information about a set with just endpoints. It gives the left endpoint, it gives the right endpoint, and then whether it's a parenthesis or a square bracket tells us if we include or don't include the endpoints. So you might have noticed I was doing graph examples that were just x is greater than, x is less than. And when I jumped to showing this, I went to a compound inequality. I went to one that had two numbers. And the reason I did that is because it was easier as a first example to do one like this. What do we do when there is only one endpoint, though? So I was showing something like this. This is x is greater than 3. I can see the first endpoint is a 3 because it's an opening parenthesis. But what do I put here? I don't have an endpoint because it goes on and on forever. Well, going on and on forever in the positive direction is the concept of infinity. And infinity always has a parenthesis, no matter what is over here. So if this was a 4 and it had a square bracket and it goes this way on and on forever, the square bracket goes with the 4, but the infinity always a parenthesis. And this would be x greater than or equal to 4. Or in set builder notation, the set of all x such that x is greater than or equal to 4. Inequality, set builder notation down here. But what we're going to use most often, interval notation. If we had a number line with everything shaded, that would be going to infinity on both ends. Oops. That would be all real numbers. And this negative infinity, that's what we use for infinity on the left side, going in the negative direction forever. So this here, we would have a closing endpoint, the second point of -2. It would have a square bracket with it. But since it's on and on forever to the negative direction, it's going to begin with a negative infinity. Negative infinity always takes a parenthesis. Let's do another compound. If in set builder notation we are given the set of all x such that x is between -4 and 2, including the 2, What would this be on the number line? What would this be in interval notation? Well, the number line between is always leftmost value here, rightmost value here. We are not including the -4. We are including the 2. And I like it with the parenthesis and the square bracket, so we can jump straight to parenthesis, square bracket, -4 and 2. So there's interval notation. The interval from -4 to 2. This interval is a set. What if I wanted you to express in words this? Well, to help you get to words, you can go through symbols. This, we know, would graph like this. And we can recognize that as x is less than -4. So we might want to say -4 exceeds x. One of those things from the beginning. Or -4 is greater than x, or x is less than -4. X does not exceed -4. By translating our interval notation to the regular inequality, we can then speak these intervals the same way we did the inequalities. What about this one? What's this one in words? Well, we have the interval from 2 to infinity, including 2. On a number line, we'd recognize this from 2 to infinity. Ah, that is x greater than or equal to 2. So here, what were our fancy words for greater than or equal to? This would be x is at least 2. Or x is no less than . Two. And by the way, look, no less than literally means not less than. So no less than and not less than mean the same thing, because if you're not less than, you're greater than or equal.